Hey, welcome back everybody to another lesson. Sorry it took me so long, but I had to do some earthquake hit reviews first, but we're back to learn with earthquake, dude. This is lesson 4, seismogram versus seismograph. Don't forget to follow me on TikTok, Twitter, and Instagram, earthquake_dude. But without wasting any more time, let's get into today's lesson, which is a good one because I'm going to teach you the difference between a seismogram and a seismograph. So, oh shoot. Okay, there you go. All right, so what is a seismograph? So a seismograph is the instrument that records earthquake shaking. Now, this is an old school one, right, with the pendulum, and when the ground shakes, the pendulum swings and creates the little squiggly lines, which are your seismic waves being recorded. Now, a seismogram is the record of the earthquake shaking that is recorded by the seismograph. I know they're very similar, but there is a difference. Gram and graph, right? Squiggly lines equals seismogram. Instrument recording squiggly lines, seismograph. Okay, I hope that helps. So what is the actual difference and how can we tell? So seismographs allow us to improve on the modified Mercalli intensity scale, which is the video that we did in lesson 3. I talk about the modified Mercalli and how it uses human observations to record shaking depending on your location. Now, the problem with that scale is that it's very subjective. Like I said, you and I can describe the same earthquake in the same location very differently. And there's also the problem that there is no data where people don't live. For example, the middle of the desert, right, where no one lives, where the Goonies live, right? Just kidding. So how do we improve collecting data on those? Well, we can install seismographs. Now, seismographs can provide an objective measure of the shaking for how strong, how long, and all these other different components. And they can be installed in remote areas, exactly where we're missing data. So, using a combination of both the modified Mercalli scale and the addition of seismographs, we can get a pretty good idea on and good data collection. So, what if we applied both of these to our theoretical scenario of the magnitude 7.8 earthquake on the southern section of the San Andreas Fault? This is the shakeout scenario. You can see very close to the fault and parts like of LA, San Fernando Valley, Bakersfield see extreme shaking based on the modified Mercalli scale. So this helps us with the installation of seismograms and the modified Mercalli scale. We get a good sense of how things are going to look after the next earthquake, right? Which is why we say over and over again, it is critical to prepare. So again, and some of the limitations include a measure of strength of shaking, right? So these seismographs can record the earthquake shake, give you a lot of good data, but it doesn't give you that single number for the size of the earthquake, and that's what everybody wants, right? Oh, earthquake here. What was the magnitude? Right? What's the number? Right? And it's like, do you even know what that number means? That number plays a role, obviously. Sometimes we don't know what that number means. Oh, I'll let you know. Okay. So let's play a little game here. We got two earthquakes. Just don't look at them. Just look at the colors. Look at the bright colors, right? We have the Northridge 1994 earthquake here on the left-hand side, and then we have the Hector Mine earthquake in 1999 on the right-hand side. Which one was a bigger earthquake, energy-wise? Meaning that magnitude. Which one was higher? I'll give you 2 seconds. If you said Northridge on the left-hand side, you're incorrect, because Northridge was actually a magnitude 6.7 earthquake, while the Hector Mine was a magnitude 7.1. So talking about energy, the Hector Mine earthquake was much, much bigger. Well, I wouldn't say much bigger, but it was definitely bigger than Northridge. But based on the subjective data collected, meaning people's experiences of that earthquake, it looks like the Northridge earthquake. And also, what plays a big role in this is Northridge happened underneath the city of Northridge, while Hector Mine happened in the middle of the Mojave Desert. That also plays a role. So, what size was the what was the size of the Northridge earthquake? it had stronger shaking because it was underneath the city town, right? Closer to the city. But the Hector Mine earthquake actually affected a large area. But it wasn't as intense. So you can see Hector Mine earthquake, people felt it all in Vegas, Lake Havasu down in Southern California, like Southern California, Ridgecrest, and parts of the northern section of California, or central section. While the Northridge one felt much more locally, right? So these things play a role, and again, just using the intensity scales of like a modified Mercalli or just seismograms doesn't tell us that number or that magnitude. Okay. So we used to use this thing called Richter scale, and I know you guys have heard it, but we don't use it anymore. We actually use things like moment magnitude. But for the simplicity's sake, we're just going to talk about magnitude. Okay. Now, what does that number actually mean? You hear, oh, that was a magnitude 7 earthquake, a magnitude 6 earthquake, magnitude 5 earthquake. Well, what does that mean, right? What is the difference between a 5 and a 6 and a 7 and an 8, right? Like, what does that mean? It means that it's complicated, right? And the magnitude scale is actually on a logarithmic scale, meaning it jumps in orders of tens. So each step on the magnitude scale represents 10 times stronger shaking than the next lower. So that means a magnitude 5 earthquake is 10 times stronger than a magnitude 4. That means a magnitude 6 earthquake is 100 times stronger than a magnitude 4. A magnitude 7 earthquake is 1,000 times stronger. Or you guys catching my drift here? It's a pretty big deal. Now, that's earthquake shaking. When we're talking about actual energy released by that earthquake, 32 times is the number. So magnitude 5 earthquake produces 32 times more energy than a magnitude 4. A magnitude 6 produces about 900. Well, it's actually 1,000 times more energy than a magnitude 4. And a magnitude 7 produces 32,000 times more energy than a magnitude 4. Now you can see how these things are getting crazy big the higher in magnitude. So using seismograms and these intensity scales and these equations for shaking and magnitude and energy release, we can locate the hypocenter and calculate all these using this instrument, seismographs, right? So here's a cool kind of anatomy picture of a typical fault, right? You have a fault scarp, you have the fault plane. So the focus or the hypocenter is where the fault first begins to rupture. Right? So it breaks from that point and it propagates along the plane of the fault. Now, directly above the focus or hypocenter is the epicenter, and that's the star that you see after every big earthquake. That's the epicenter. Yeah, and you can see these are those seismic waves that are being. So here to put it, the point where the fault first starts to slip. That's the hypocenter. It's always below the Earth's surface on the fault plane, and the epicenter is directly above that. Right. So when we talk about epicenter, we're looking at the point above the hypocenter on the Earth's surface. So all maps will show epicenters, but that's not necessarily where the fault first begins to rupture. I hope that makes sense. So how do we locate the epicenter of an earthquake? Well, you're gonna need to learn about the different types of seismic. And to do that, you're gonna have to subscribe. That ends lesson 4. So if you guys have any questions, please leave them in the comments below so I can clarify anything. Like always, like, comment, and subscribe means the world to me. We're so close to 200 subs, guys. Hopefully by the time this video goes up, we're 200. I cannot thank you enough for watching. Lesson 5 will drop very soon. Much love. Thank you for watching. I'll see you guys. Bye.